Why don't we start with everyone typing in their name and email address in the chat.
I'm wrong with the
Okay. All right. So today I'm going to start chapter 10 because it's very, very similar to chapter 9, but I will also go back and do a couple more problems in chapter 9. Okay. So you'll see that it's really almost the same thing. It's just one is with strain as opposed to stress, which is what we do in chapter 10. Okay. All right. Does everyone put in their info into the chat? Yes, no? All right. Okay, so do I have that slides deck set up? Yep, I do. Okay, so let's talk a little bit about chapter 9. And like I promised, the first problem we'll talk about chapter 10, but the first problem I'm going to do, I'll go back and I'll do a chapter 9 problem as well. So if I can share my screen. All right, so chapter 10 is strain transformation, okay? So there is one thing that's a little bit different with it. And let's see if I can get this. Just chill out. Oh, Zoom always blocks the ability to do everything. It's weird. Okay, there we go. All right. So we're going to talk about transformation of plane strain, which will be very, very similar mathematically to the transformation of plane stress. The only one thing is when we did plane stress, we had the shear stress tau. When we do plane strain, we're going to have the shear strain gamma. But this is kind of a weird thing. Mathematically, the correct concept from a tensorial standpoint for strain is actually gamma on 2. So everything will look the same except all the shear components will have a 2 division, and that's going to be with the explicit equations and Mohr circle. Okay, so we'll talk about the transformation equations. We'll go over Mohr circle, which will again be identical. I'm just going to do these today, and then next class, or maybe I'll flip it, we'll do the strain gauges and then talk a little bit about Hooke's law. So strain gauges are a very important thing, and we'll talk about those, right? You really can't measure stress directly. Experimentally, almost all stress measurements are evaluated with the use of strain gauges, which are little metal foil sensors. They look almost like a piece of gum wrapper, right? And embedded on them, you have piezo resistive material. So if you stretch the material, the resistance changes, and you can figure out very precisely how much it stretches or how much it strains, because you know the length initially. And then from the strain, if we know how the strain is related to the stress, ergo Hooke's law, we can then calculate the stress. And this is how it looks. As I said, 99% of all structural experiments where they calculate the stresses, that's how it's done, okay? But today we're going to just talk about the strain transformations and Mohr circle, and it's all going to go the same way. we're going to have principal strains. We will have maximum in plane shear strain and also maximum absolute shear strain, okay? Just like with stress. Now, these things go the same. Actually, we don't really talk about it much at the undergraduate level, but stress and strain are mathematical quantities called tensors. You've actually already seen tensors before. A vector is in fact a first order tensor, or sometimes called a rank 1 tensor. A vector, we know, has a scalar value and a single direction. So like your velocity vector, it has a speed, that's the magnitude, and there's a direction that you are going in or the object is going in, right? And that's a vector, a first order tensor. We're all really comfortable with those. Stress and strain are what we call second order tensors. They're really the mathematical entity that describes stress and strain, and that has a scalar value, a magnitude, and 2 directions. So with stress, the 2 directions are, one direction is the plane that we cut the body, and the second direction is which component we're talking about. So when we talk about like the tau x y shear stress, this is one direction and this is another direction. The x direction is the cutting face, and then the y is the component. For strain, it's the same deal. The 2 directions. One direction is in what direction are we looking at the change in stretch, and then the second direction is which direction is it actually stretching in. So for shear strain, like if you look at this shear strain angle, in fact, the actual motion is in the y direction, but it changes with respect to x, and that gives you a shear strain. A normal strain changes in the x direction, the x displacement, okay? And so those are, again, 2 directions, a single magnitude, okay? And they mathematically transform in all the same way. So that's why all this math is the same, all right? And I don't know what happened there. Well, there you go. Okay, so we had the equations for stress transformation. There they are, right? And so if we were given the stress state, sigma x, sigma y, and then the shear stress, and then we were told how much is the planar rotation to the new coordinate system, theta, we were able to determine the normal stresses and the shear stresses in that rotated coordinate system, in that new frame of reference. The strain is identical. It's identical here, except that if you look at the shear term here, here, and here for the stress transformation, if you look at that term in the strain transformation, as I mentioned earlier, it has the engineering shear strain gamma divided by 2. And that's because mathematically, really, this quantity gamma on 2 is the correct tensorial quantity. And that's why we call gamma the engineering shear strain, because it's really not the correct mathematical shear strain from a tensor quantity, but it's what we use in practice. So we just have a 1/2 kicking in here. So that means if you're given a problem where they give you the state of strain, normal strain in the x and y direction, and then the shear strain, and they say figure out the strain components in this alternate coordinate system given by the rotation theta. Again, all you have to do is plug those values into equations 10, 5, 6, and 7, and that'll give you the normal strain in the x and y direction and the shear strain over 2, right? in the new coordinate system. Okay, so same as stress, just don't forget to divide the shear strain by 2. All right. Okay. Also, you can do Moore's circle for strain. And again, everything's the same deal. Okay. Don't want to skip forward. Right. We have the normal strain on the x-axis and the shear strain on the y-axis, but it's the shear strain divided by 2. Again, for the same reasons, right? Mathematically, that really is the correct component of shear strain, okay? And it's a circle whose center, again, is at the average normal strain and has a radius, again, very similar to what we do for Moore's circle for stress, but again, instead of the shear stress squared, it's the shear strain over 2 squared, okay? So it's identical. And then, of course, you can probably imagine what's going to happen next. Since we have Moore's circle, we can figure out if we have a certain state of stress like here and here, we can figure out how do we rotate into a strain state on the x-axis where there are no shear strains, and this is the principal strain state. As it turns out, for isotropic materials, the principal strain state, of course, corresponds to the principal stress state. So, you know, we know that the shear stress tau is equal to the shear modulus times the shear strain. So if we're in a principal strain state, gamma goes to 0. And if gamma goes to 0, obviously the shear stress goes to 0. And so you have to be in a principal stress state as well, okay? So that's always, they're always going to be the same orientation, right? And then again, we can also look at the points top and bottom where we have the maximum in-plane shear strain. Now, in that particular state, as with max shear stress state, you will have a normal strain, right? It's actually going to be that average normal strain. And it may or may not be the max absolute because, as we talked about also in shear stress, you have 2 other out-of-plane Moore circle. And in this case, you would have the maximum absolute shear strain up there, which would be the radius of this larger circle, which is, you have to always be a little careful about the gammas on 2. So this radius here is half of the normal strain, and then that equals to this distance here, which is actually the y coordinate is gamma on 2, so you actually have twice that, right? So anyway, okay. So it's identical. So that's why I kind of don't want to spend too much time on it. You can do it the same way. Here's the, yeah, this is what I'm just talking about, okay? And this is all the same. Okay, let's not talk about strain gauges yet, except, you know, I did talk very briefly in the beginning, so at least I'll show pictures of them. Here is an actual application, how you would use strain gauges, right? So in this particular example, they have this column here that's loaded up, and I wonder, looks like they're here, but it's hard to tell. Located on there, they glue these little foils of piezo-resistant material that as this structure deforms, as it strains, they're able to measure the normal strains in these 3 directions. And from that, they're able to calculate this full strain state in the plane. Oops. And we'll talk about that next class, okay? All right, so obviously from there, they use Hooke's law and they calculate the stress from the strain, okay? All right. Is there any questions on that with regard to at least the strain transformation and Moore's circle principal values of strain and all that? I think again, like it's pretty simple, you know, so it's the same as the plane stress, okay? Like I said, I'll do some examples right now, okay? So the first example I wanted to do is problem 981, and that is a so that is a stress transformation problem. So let's look at that. 981, I think that's this. Yeah, I can't tell. Whoop. Whatever this is, I don't know what this is. 981, yeah, that's 981. All right, so here's a state of stress. It's planar. You can see there's no stress components in the x direction. All right, it's normal or shear. All the non-zero strain components are in the y z plane, right? They're all in here. And this particular problem wants us to figure out the principal stresses and the absolute maximum shear stress. So let's do that. Let's indulge the book. Okay. All right. So what do we have here? Okay. Again, for these, I think it's easiest to do Moore's circle. So we have this 10 KSI. That is a normal stress in the z direction. Okay. We also have a normal stress in the y direction. That's the 20 KSI. And there is a shear stress of 8 KSI. That is in the ZY plane. Now, if we look at that technically, this here is a positive Y face. And since this shear traction is acting in the positive Z direction, that is a positive shear strain. So it's a positive 8 KSI shear strain, okay? The normal stresses are positive. They're tensile, not compressive, okay? All right, so let's do this. Okay, let me draw some Moore's circle axes, okay? So let me just kind of scoot over here a little bit. So here's our x-axis. Pretty much everything is going to be on the positive side. So let's put this like this way. Okay, so this is going to be the normal stresses on the x-axis. We'll put the shear stresses on the y-axis. And again, the convention is such that if the shear stress on the face rotates the little cube in a clockwise manner, that's positive up. All right. Okay. So let's plot the normal stresses first, we'll first do this face here, right? We'll first look at that face. And so on that face, what do we have? We have a normal stress of 20 KSI, right? So let's say this is 10, 20, 10, right? Minus 10, sort of, right? So the normal stress of 20 KSI, so we'll be here. And then the shear stress on that face is 8 KSI. And that wants to rotate it in a clockwise manner around the x-axis, right? If we do a right-handed rule, that is a, I'm sorry, it's rotating at a, how do we say that? It's positive, but it's rotating in a counterclockwise manner around the x-axis, okay? So if you look down the x-axis, you see y and z. Here's the little stress cube, right? So we get 20 KSI in that direction, 10 KSI here, and then the 8 KSI rotating as shown, right? So this is looking down the x-axis. So the 8 KSI wants to rotate it counterclockwise about the x-axis. So that's going to be in the negative direction. So that's about here, let's say. So that's on that positive Y face. Right, so the point there is 20 minus 8. Okay, all right. Now let's go and look at the top face here, which is on the positive Z face. There again, we have a positive 10 KSI, so that's going to put us here. And the shear stress on that face wants to rotate it clockwise. So that's going to put us up about the same amount, right? So there you go. So there's the second point. All right. So this is the point here on the positive Z face. And it's at 10 positive 8. Okay. So now we have the circle, right? We can draw here's the radius of the circle connecting the 2 points up. And go away. Okay, let's do that. I just lost it. Where'd it go? There it is. Okay. And then let's try it. So, okay, so this point here is the average. So clearly this is at 10, this is at 20. So the average right here is at 15, right? That is 15 KSI. Okay, so let's get the radius. So we know this distance here is 5 KSI, and this distance here is 8 KSI. So the radius of Mohr circle is the square root of 5 squared plus 8 squared, right? So again, it's kind of nice because you don't really have to memorize those equations. You can if you want to, but it's, you know, I think everybody knows how to do this bit, right? So that gives me a radius of 9.43 KSI. And so that will actually kind of put us out about here and here, if I draw this correctly. So on a piece of paper, you can get a compass or something and draw this better than I can do on this tablet. But that is Mohr's circle. All right. These 2 points correspond to the given state of stress. All right. So first we wanted to figure out the principal states. Okay. So those are going to be here and here, right? So this is sigma 1 and sigma 2. So we're going to consider that like in ascending order if you want. All right. So sigma 1, the first principal stress, is going to be the midpoint, 15 KSI, minus the radius, right? Minus 9.43. And that gives me a value of, oops, come back here. Oh. 5.57. And, you know, I didn't do a great job drawing it, but that's kind of close. That looks about 5.57. So that seems to be a reasonable check. Okay, that's the first principal stress. The second principal stress is going to equal the average normal stress, the 15, plus the radius, right? The center point plus the radius. And that equals all right, so that gives me a value of 24.4 KSI. All right, that's good. And we should also say, okay, in what orientation is that? So to get that, we would rotate from this position up by half of this angle, right? Remember, the angles are all doubled. So this is the rotation angle to get us into the principal strain location, okay? So well, let's do down here, I guess. Let's do down here. So this angle 2 theta principal, the tangent of that, or let's take the inverse tangent. It's going to be the inverse tangent of the rise, which is 8, over the run, right, which is 5. And you want to be careful about the quadrants and all that stuff in here, right? Because whenever you take inverse tangent, you know, because of you could have 2 negative signs or 2 positive signs, but actually get the same angle. So the quadrants could be off by 180. So you just want to be, you know, that's where the picture of Mohr circle helps a bit, right? Where's my inverse tangent function? Here. All right. And so that is 58 degrees. Or if I take half of that, that gives me that theta P is half of that, which is 29 degrees, right? Okay. And this is a rotation. So remember, strain, you can't use degrees for shear strain, but for rotation, you can use degrees. Okay, well, it's acceptable. All right, so that means that actually, visually, if we were to draw the cube in its rotated state, right, the principal state, it's going to be rotated in 30 degrees, right? So basically, kind of going to look like this. It's about 30 degrees. I guess I could use that little thing to, okay, but of course it wants to do that. All right, so this is rotated 30 degrees, or I should say 29 degrees. What am I talking about? 29 degrees, right? This is the principal orientation. All right, so this face here, okay, which was the positive Y face, which corresponded to that point right there, that rotates up, and the normal stress on that face will be the second principal stress, sigma 2. So that one is going to have the larger stress. That's going to have the 24.4 KSI stress acting on it. And this face here, this top face, right, this point here corresponded to the upper surface. That rotates down, and the normal stress on there is the first principal value, the 5.57. And there you go. Okay, so that's the principal state, okay? You know the values, and you also know its orientation relative to the given state, okay? There's no shear strain there at all, all right? Okay. Okay, now they want us to get the maximum absolute shear stress. Okay, so up here and here, we have the maximum in-plane shear stress. That's going to correspond to the radius. That corresponds to the 9.43 KSI. So, I mean, let's just, I know it's not asking for that, but let's just first talk about that, right? This is the max in plane. All right. Now you'll notice, okay, so it's going to exist, you know, with a shear strain of 9.43 and a normal stress of 15 KSI. And in Mohr's circle, right, it's always going to be 90 degrees from the principal state, right? The principal state is always going to be that x-axis. And then we rotate it 90 degrees in Mohr's circle to the straight up and down. Now that means the actual rotation is 45 degrees, right? Because it's always half the angle, right? So the in-plane shear state, the in-plane shear state is always 45 degrees off. from the principal state, right? Okay, so it's going to rotate. So we're at 30 degrees, and then we rotate another, I always say 30, I'm rounding up, 29 degrees, and then we always rotate another 45 degrees. So that's So that's 74 degrees, right? So it's going to be 74 degrees. So if we rotate another 45 degrees, so it's going to look like this. All right, okay, but don't do that. So that's not really well drawn, but that's, so we rotated another 45 degrees on top of the 30 degree, the 29 degrees. So that brings us to, as I said before, 74 degrees. Okay. And right, we have this at this point and this point, right? We're going to have the same normal stress. It's going to be the 15 KSI. It's positive. So we have 15 KSI. If we call that a hydrostatic stress because it's like hydrostatic pressure, like if you're underwater, it's acting the same in all directions. Sorry for drawing so poorly on this. And then we also have the shear stress in plane of 9.43 KSI, okay? And so let's just do it, right? So this face here, right, corresponded to sigma 2, right? Come on, you can slide. And we rotate 45 degrees up to this point. So that means that this face here rotates up to this face. And the shear stress on there is positive on Mohr's circle. So that means it wants to rotate in the clockwise manner. So it's going to go that way. And then its couple friends going to go like that. Okay. So that's the shear stress on the max in plane state. And its value is, again, the radius of Mohr's circle, 9.43 KSI. Okay, that is not what the problem's asking for you, but I just wanted to show that, okay? So that is the maximum in plane. We're just rotating in the plane. They want the maximum absolute, okay? So the maximum absolute, again, always exists because if, let's discuss this again. If we look at this out of plane, we have this point here on this surface where there's no components. So if we look at that point, the normal stress in Mohr's circle is 0, and the shear stress in Mohr's circle is 0 on that face. So where is that going to be? This face right here on Mohr's circle corresponds to the origin, okay? So that, whenever we have this planar stress state, you're always going to have one face, the out of plane face, is going to lie on the origin, and that's going to allow us to draw 2 more rotational Mohr circles. And so there's going to be another one that kind of goes like this. And this is going to be the one that has the maximum absolute strain. And that is not a very good looking circle, but you get the idea. Again, because they're since both normal stresses are of the same sign, you're actually going to have a maximum shear stress that's greater than the max in plane. So the absolute max is going to correspond to here. This is the absolute max. All right. Now, to get the actual orientation that is in, it's a little tricky to do. You can actually figure this out mathematically. It is a little bit annoying because we have to deal with Euler angles being transformed to directional vectors, and it's we don't really we won't really get into it. It's not in the book, and we'll kind of skip it for an undergraduate class. But suffice to say, what that basically means is you have to imagine it's, when we're going from in plane to principal to max in plane, we're rotating only around the x-axis in this problem. But this particular state here is going to correspond to a rotation that's also rotating away from the x-axis. So it's around some axis of rotation that's not corresponding to the x-axis, okay? So it's hard for me to draw those. Forget about doing the mathematical derivation, but we can still figure it out. So right here, okay, so let's figure out what's the value at this point. Okay, so this bigger circle here has a diameter equal to the second principal stress, okay? So the radius of that circle is going to be the second principal stress over 2. It's going to be that 24.4, right? 24.4 divided by 2, which is 12.2 KSI. All right. So this value up here is going to be 12.2 KSI. All right. Now, like, if we were to draw that, I don't know exactly what the orientation is, but let's just draw that, right? So we would have a shear stress of 12.2 acting on there. And in that case, it's going to kick it in the clockwise position. So again, I don't know exactly what the orientation is, but assuming it's on that face, it would look like this. All right. And then we also would have the normal stress corresponding to this point. And again, that would be at both points in the max stress, which would be, this face and this face, right? And that value is going to be, half a sigma 2 as well. So that's going to be at 12.2 KSI. So positive. So we're going to have also this normal stress here of 12.2 KSI. Okay. And that's how you do it. Now, when you ask for this max absolute shear stress, or when the book asks for it, or I ask it on an exam, again, because the geometric rotations are a little bit complicated, we usually won't ask you to display it, but this is what the components would be. It does have a shear and a normal component, right? But this is the answer we're going to be looking for, right? The maximum absolute value. The maximum absolute shear stress, okay? All right. All right. So, right. So again, more circle is kind of nice because you don't have to really memorize anything. All the equations are just basically geometrical things, so it's pretty easy. Draw more circle. The 2 points correspond to the faces. Then we can calculate the principal values, not only the principal values, but we can also figure out how we have to rotate in plane to get that. You can get the maximum in plane shear state and also the maximum absolute. If in the original problem, in the original stress state, like here, if the normal stresses have the same sign, they're both positive or negative, you're going to have a maximum absolute shear stress that's greater than the in-plane one. If they're alternating signs, one's positive, one's negative, then actually the in-plane is going to equal the maximum overall shear stress, okay? All right, any questions on that? Don't forget the 2 theta stuff, right? That's the big deal. All right, there's a couple other problems in that chapter as well that I was debating about doing. Maybe if I have some time, I'll do it. But they're like combined loading problems that then ask you to figure out the maximum the maximum shear stress or the principal shear stress values. And for example, like if there's ones like where you have a bolt, right? I don't know how to draw a bolt. That's a bolt, I guess. I don't know. Right? Can't draw a bolt. Right? So that's like a bolt. And then they put a wrench on here, like out at a distance, that puts a force. So we have one of those classic combined loading problems. So you get as we did in chapter 8, you get a planar state of stress here, right? Maybe it looks like this, right? And then from this, you can do more circle and figure out the principal values and the principal orientation, okay? So there's problems like this in the book. Like I said, this is just taking a exact same problem that we did in chapter 8, getting the result on the differential element, the little differential stress state, and then applying what we learned in chapter 9 to get the principal values, okay? So not too big of a deal. So maybe we'll do one at the end, okay? But let's do a strain one, okay? Just again, really, the strain stuff is very much the same, except we just have to be careful about the 1/2 on the strain part. Okay, so let's find a strain problem. All right, what's going on? Hold on a second, let me stop sharing. Oh, the PowerPoint really screws everything up. Now it wants me to log in. What is it doing? All right. The textbook open somewhere here. Can I find it? Where is it? Here. All right. Okay, this is a good one. Let's do this. All right, so this is problem 1022 in the text. So here we have this L bracket loaded up in some manner, who knows what, there's some loading on here probably, right? That produces a state of strain here at point A, and they give us the strain values here, the normal strains.
The screen, sir.
As the shear strain. Oh yeah, thanks. Sorry about that. I'm not sharing. I was never good at sharing in school, so it's not surprising now. I have the same difficulty. Okay, so and then they give us, the normal strain out of the plane is 0 as well. If you're not given other components of strain or stress, you can, it's reasonable to assume that they are 0, right? Like if they only give you a couple of components of stress or strain, the assumption is that the other components are 0, okay? As are sort of given here, they give you the normal strain in the Z, but they don't give you the gamma ZX and the gamma ZY, which again, I would assume also 0 here, right? If they're not, we're going to have a difficult time doing the problem. And here they want us to find the principal strains at A, and then the maximum shear strain in the XY plane, and then the absolute maximum shear strain, okay? Right, and in this case, the answers for B and C will be different. Okay, so let's use more circle on this one, all right? Let's draw a set of axes at least. Everything here is positive again as well. Oh, come on. All right. So here we're going to put the normal strains on the x-axis, and on the y-axis are the shear strains. But remember, shear strains divided by 2. So always remember it's divided by 2. And it's going to be positive such that it rotates the cube in the clockwise direction. So let's just talk about that a little bit. Okay, we'll talk about that a little bit. All right. So there's our axes. Let's visualize this. All right. So if we had a component like this, all right, I'm going to draw it in the XY plane. So let's see if this will make a cube. That would be nice if it does. Good, it did it. All right, so I'm going to draw the deformed cube in blue. All right. So we have a normal, positive normal strain in the X direction. So it's going to stretch. I'm going to exaggerate this, right? So it's going to stretch in the X direction. Okay. So like that. And then it's also got a positive strain in the Y direction. So it's going to stretch in the Y direction. It's going to stretch more in the Y direction than it does in the X direction. So I'm going to draw it a little bit more. I'm going to try to eyeball scale it. And we have a negative shear strain, right? So we know the shear strains make them look like trapezoids, right? So like if we don't have this shear strain, if the shear strain were 0, we would just have this sort of volumetric shape kick in, right? It would still be a rectangle, but obviously it would no longer be a square. All right, so how does this go? Well, this is a negative shear strain, so that comes from a negative shear stress. All right, so which direction is it dilating? Well, this comes from a negative shear strain. I'm sorry, negative shear stress, right? Because the shear stress is proportional to the shear strain. And on the positive X phase, on this phase, that would correspond to a shear traction acting down, right? This would be the negative shear stress. I'm drawing them inside the cube just to keep them out of the way of everything else. That would be a negative shear stress, right? And how's that going to make this deform, right? That is going to take this side and kick it down. So you're going to end up with something that kind of looks like this point kicks down. So it's going to look like the following. I'm exaggerating a little bit, right? But that's kind of the way it would go. Does that make sense? Now, I don't know. Let me see if I can kind of draw this on here. So maybe I can do it with the ruler. Maybe I can do it reasonably. Oh, I could have if I. Hold on a second. I always have to pause. You guys don't know why I always pause, but it's because as soon as my pen gets near the screen, the zoom controls take over everything, and I can't write on this stupid whiteboard anymore. So, okay, fine. So that's why I always pause, and it's really frustrating for me. And you don't see it, but whatever. So the strain is going to look something like this. Probably this is very much exaggerated, right? Because, these things are all to the -6, right? These are all in microstrain units. But you could go out. I mean, if you really wanted to, like I won't do it here, but you could go and do all the trig and figure out exactly what the angle change is due to that shear strain, right? But ballpark, this is what we got, okay? And so the point is here on this face, we have a shearing strain that wants to go in the clockwise manner, okay? So that's actually going to be a positive value, okay? So that's the other reason we want to do this, so we know which way it's going. So on this face, it's going to be positive shear strain. On this top face, it's a negative shear strain, okay? Does that make sense? That's the most important thing, to determine which is positive and which is negative. Honestly, if you get it wrong, you still get the same Mohr circle. It's just your angles will be off, okay? All right, so let's draw the points now, okay? So let's draw the points, okay? So now we got it. All right. So we have the two normal points. We have one at minus, no, I'm sorry, they're both positive, 300 and 550. So let me just kind of tick off some points here to try and be reasonable. So let's say this is 100, 200, 300, 400, 500, 600, 100, 200, 300, 400, 500, 100, 200, 300, 400, 500, 100, 200, something like that, okay? All right, the point corresponding to this face here in blue, right? That has a normal strain of positive 300. So we're going to go to 300 right here, okay? And as I said before, the shear strain is in the clockwise rotating direction on that face. So it's going to go up. Okay, it's going to go up 650. But remember, we have to divide by 2. So that's 325. So we go up to 325. 100, 200, 300, 325. So that puts us about here. Okay, so that's that blue face, right? This is going to be at X value of 300, Y value of 325, right? Again, because it's the shear strain over 2, right? Okay, now let's do the second point. This face, we'll do face here, and I'm going to note it in purple, okay? So that has a normal strain of 550, so it's positive. So 400, 500, 550 puts us about here. And the shear strain wants to rotate this in a counterclockwise manner, so that's going to go down. Again, we divide by 2, so we go down 325. So that puts us about here. Okay, so that's that face, 550 minus 325. And now we can, draw the radius of the circle. It's going to look something like this. And maybe kind of try to draw this circle. So looks like we'll be up about there. Here. So maybe it's something like this. All right, so there's roughly Mohr's circle for that state shown, right? Okay, first they want us to find the principal state. Okay, so the principal state is going to be, right, going to be here and here. So we rotate this angle, which is twice the angle to get me to that principal state. Okay, so this is the principal state. There's going to be no shear strain. There's only going to be normal strain, epsilon 1 and epsilon 2. So this center point here, right? The average strain is 300 plus 550 over 2, right? And again, I'm dropping all the micro strain stuff, but obviously it's there, right? So that is 375. Right, that's technically microstrain units, right? Okay. And the radius, let's get the radius of Moore's circle, right? So whatever, let's do this point, right? So this distance here is going to be the 550 minus the 375, right? So this distance here is 550 minus 375, which is 175, right? So the radius of this circle is going to be 175 squared plus, the shear strain over 2, but that's what we got here, right? This is the minus 325, okay? But it's going to be squared, so it doesn't matter, right? Minus 325 squared. Okay. So the 1/2 is in there because I already took the 1/2 off when I got the minus 325, right? It's half of the 650, right? Yeah. All right, so radius, 175 squared, 325 squared. All right, that gives me a radius of 369 microstrains, right? Okay, fine. So that means that, oops, I'll call these both epsilon 1. This should be epsilon 2. So that gives me epsilon 1 is going to be 375 minus 396, which is positive 5.88. So my Mohr circle doesn't look quite accurate there. It's really much more over to 0. And then the second principal value is 375 plus 369. Right? Let's make sure I calculate that radius the right way. That's it. Okay. All right. So this gives me a value of 744 microstrains. Okay. All right. So those are the principal values. And let's get this angle, right? So 2 theta principal is the inverse tangent of 325, the rise, right? This leg here, 325 over 175. And that gives me an angle of 63.56 degrees, 63.6 degrees. So that rotation is half of that, which is 31.8. Okay, so we're going to rotate the state of stress counterclockwise 31.8 degrees. So in fact, that orientation is going to look like this-ish. It's about, well, maybe it's a little less than 30 degrees. 30 degrees would be a little bit more than that, but whatever. Let's say that that's it. So in that case, we have two normal strains, no shear strain, so it's going to stay rectangular. All right. Most of the strain is going to be on the epsilon 2 face. So this was the purple face right down here, which is this top face, right? So we have originally the top face corresponds to this. So that rotates 31 degrees into this orientation. Oh, come on, don't do that. So it's on this face that we're going to see the epsilon 2 strain. So we're going to see the maximum strain. So it's going to really stretch in that direction. The other face stretches as well, but it's only by the 5.88 microstrain. So it's almost nothing. So it's going to look, it's like this, right? So the way this actually deforms in that principal state is going to look like this. Okay? So it's going to stay, if you were to draw a little cube of material with a magic marker in this orientation and then strain it as shown in the picture, it would still be rectangular. It would stretch into this dimension. So it would stretch mostly into the Y direction and a little bit in the X direction, okay? All right, so that's the principal state. Now they want us to find the maximum shear strain in the XY plane. So that's the max in plane. That's going to correspond to here and here. This is going to be max shear strain in the XY plane. Okay. All right. And again, that's going to have a value here where the normal stress is 375 and the shear stress is the radius, which is going to be the 369, right? So for part B, all right, I'm sorry, let's be careful about this. The max shear strain over 2, this is in this. That's going to equal the radius, right? So, which is, what was it, 369, right? Okay, and so that means the maximum shear strain in the XY plane is going to be twice that. It's the diameter of the circle. So that is 738. All right, so there, we don't want to forget the -6, right? So that's the answer for B. And then finally, if we're going to do the answer for C, right, they want the max absolute. All right, the max absolute shear strain. So in this case, again, we have the 0 out of plane point corresponding to the origin. And so now that's going to generate the 2 other rotational Mohr circles. All right. And so from this, now we can clearly see up here, this is the max absolute. Okay, that's the max absolute shear strain. And that's the radius of this circle. So this circle here, this bigger circle, this one has a diameter equal to epsilon 2, right? Okay, that's not epsilon, that is 0. So that is the 744, right? Okay. And so the actual radius is going to be half of that. Well, it's a pretty easy. So the radius of the circle is half of that, right? But then we're gonna have to multiply that by 2 because, right, we've got the over 2 on axis. So you actually end up with the same thing. So the answer for part C, the max overall, is going to equal 744 times 10 to the minus 6 strain units. Okay. And so it's very close to the in plane, just a little bit out. Okay. Just a little bit out, but it still is greater. Okay. And those are the answers for that one. All right. Any questions on that? Like I said, another type of problem you could be given is like it could give you this shear strain state. I'm sorry, this strain state here. And it would ask you, okay, consider this the strain state for a coordinate system rotated by 15 degrees. Okay. And in that case, you could also use Morse circle. But I think actually for those types of problems where they want you to find it in a particular orientation, not the principal or the max shear, the easiest thing to do there is just plug it into those equations, okay? And so that one's pretty straightforward. I will not do that. All right. Okay. I got a little bit of time, so let me just start the strain rosette stuff. At least I'll kind of just talk about where it comes from, all right? Okay. Let's clear this out. Okay, let's talk about strain rosette. Okay, so we're gonna have a strain rosette. There's a lot of different orientation these things can happen in, okay? Do I have pictures in my slides? I don't know. Let's see. Let's see if I have them. All right, so you're seeing the slide deck now, I believe, right? Okay, well, you, what did it just go away? All right. Okay, I have to open it up again now. As soon as I went to go share it, it decided to close it. I don't know. Oh yeah, here we go. Oh, I think this has all the math. Oh, this is better. Okay, I think the slides are good for this anyway. At least to get it started. I'll just give you the idea that what's going on here. Share screen, right? Share screen. Okay, like I said, here is a example of a strain rosette. We showed this last time. Okay. In the Lockheed Martin lab, we have a whole setup that does some very, as strain gauges on various structures, and it works the same way. And there they show they talk about the strain gauge factor and pass it through a Wheatstone bridge conditioning system, and so you don't get temperature variance and all that sort of stuff. There's a whole art to this, even to just gluing these little strain gauges onto the structure itself is a whole thing unto itself. Okay. So I don't want to get into all those details, but let's talk about the, as an engineer, what do you need to know? Okay. So I think I have some different ones. So they come in a variety of orientations. So for example, this one shown here would be called a 04590 strain gauge rosette. And the reason is because if we rotate it 45 a little bit, right, into this orientation, we can measure strain along the 0 axis, strain along the 90-degree axis, and then the strain along like a 45-degree axis, right? I guess you could also consider this plus minus 45, 90 as well, okay? There are other ones. Oh, here's some other ones. Here are ones. Here's one that's, again, 45. This is like what we showed in the previous slide. There are also ones that are offset by 60 degrees. So there really is no preferred orientation, okay? And, they can come in a variety of different orientations. I mean, the book talks about them being in these arbitrary three angles, theta A, B, and C, but typically, they're usually one of these two orientations, okay? Now, let's just look at this particular case here. So this strain gauge here on A, that strain gauge reading is going to equal the normal strain in the x direction. That makes sense, right? Because its strain etchings are lined up with the x-axis. Likewise, this one at C, that would give us the normal strain in the y direction, right? And then we have this third one here at B. It might be really nice if epsilon B, the strain gauge at B, measured the shear strain, but in fact, it does not. It does not measure that. It measures the normal strain along this 45, okay? It does not measure the shear strain. So we need to get that, right? So in particular, for this 45, we can get the normal strain in the x just by reading the strain gauge A. We can get the normal strain in the y direction by reading strain gauge C. But somehow we need to use the strain gauges to calculate the shear strain. That should be a gamma, right? This should be a gamma. Shear strain in the plane, okay? So how do we do that? Well, that would be a stress transformation equation. Okay, okay, I don't do it. Okay, so let's do this one. Let's just do this one. Then I'll stop in a second. So we already know. Okay, so we know that. Okay, stop. Don't do that. We know that epsilon A gives us the normal strain in the x direction. We know that epsilon C gives us the normal strain in the y direction. All right, but what are we going to do with epsilon B? All right, so I'm going to put a new coordinate system here, like this, x prime and y prime. So in this particular case, obviously, the strain gauge at B, that gives me the normal strain in the x prime direction, right? It's the normal strain in the x prime axis. All right, so how do we get that, right? Well, we can use our stress transformation equations, which I kind of forget. So epsilon x prime is epsilon x plus epsilon y over 2 plus epsilon y. I gotta look it up. I forget. I forget whether it's plus or minus, but then it's like the difference of these. Oh, stop. What is it doing? Let me look up. I forget. I have to always. All right. It's the minus x minus y over 2 cosine 2 theta. And there we go. So it's and then plus gamma x y over 2 sine of 2 theta, right? Those are just the stress transformation equations, okay? So in this particular case, I know epsilon x prime, that is the strain gauge at B. We know the normal strains here because those are at A and C. We know the angle is theta is 45 degrees. So 2 theta is 90. Cosine of 2 theta is cosine of 90, which is 0. Sine of 2 theta, sine of 90 is 1. Okay, so that goes to 1. And I don't know this, but that is what I want. So now I have epsilon B equals epsilon A plus epsilon C over 2 plus gamma x y over 2. And I can use this to get gamma x y equals 2 epsilon B plus epsilon A plus epsilon C. And I screwed up a sign here somewhere. What did I do? This should be a minus, right? This is minus this. Correct. I did that correct? Let me just make sure I got the signs correct before I go on. Right. Minus plus gamma. Oop, where are we? Right. So that's right. So now this is how you calculate the strains. The normal strain in the x direction is what you read off of this A strain gauge. The normal in the y is what we read off of the C strain gauge. That's a C. And we can use this relationship here to calculate the shear strain. Okay. And so now you have all shear strains. There's, you got a different result for the 60-degree strain rosette. And I posted the derivations for all these, and they're on Blackboard. Okay. All right. They're also in the textbook as well. Okay. Let me stop there then. All right. I know that was a lot of material, but if you read through it, you'll find it's really not that hard to do. Okay. It's a lot of plug and chug stuff, but just be careful about the over 2 on the shear strain stuff. Okay. That's the only thing you gotta be careful about. The shear strain is 1/2. Okay. All right. Very good.